Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We have been going through a course of lectures on optics, and now we are going through the section on interference. The contents of this lecture will be air wedge, expression for the fringe width, expression for the thickness of the wire, Newton's rings, experimental setup, and the expressions for the radii of the bright and dark rings which you obtain in the Newton's rings. Let us now go back to the case of air wedge. We saw in the previous lecture how a wedge shaped film can be produced, that is, by introducing a thin wire you get a wedge shaped film as is shown here, and you have a point x m where you get the mth dark band or fringe, and x suffix m plus 1 refers to the point where you get the m plus 1th dark band, and the thicknesses which correspond to these points. The thicknesses what? The thicknesses of the air film or air gap or T suffix m and T suffix m plus 1. We assume that at these points we get the mth dark band and m plus 1th dark band. So, obviously, this distance will be the band width. It is a distance that separates 2 successive bright fringes or 2 successive dark fringes. You have got the mth dark band, m plus 1th dark band. So, obviously, this distance that separates x m and x m plus 1 give you the fringe width. After having got the expression for the fringe width, we will see how the diameter can be expressed in terms of beta, the fringe width. Using this expression, it is possible to determine the diameter of the thin wire, or which cannot be measured by other methods, say using screw gauge or vernier caliper. Very thin wires, the thickness of thin wires or even the thickness of thin paper can be measured by the air wedge experiment, which makes use of the phenomenon of interference. This is the beauty of the phenomenon of interference, by which the thicknesses of a hair or a paper can be measured. So, we had the expression for the thickness of the film that you get corresponding to the mth dark band, 2 T m is equal to m into lambda. Similarly, the m plus 1th dark band, the corresponding thickness of the air gap is T m plus 1, 2 times T m plus 1 will be equal to m plus 1 into lambda. Subtracting the above 2, obviously, we will be getting an expression of this kind, which is shown at the bottom, 2 times T m plus 1 minus T m will be equal to lambda, because m plus 1 minus m will be 1 times lambda. You got the expression here. You have here the mth dark band, m plus 1th dark band, d is the diameter. Now, your T m plus 1, right, that divided by x m plus 1 will obviously will be also equal to T m divided by x m. Okay. The angle that is obtained is same, right, the average is obtained. So, whether you correspond to T m plus 1 or T m, the thickness of the m plus 1th dark band, the thickness of the air gap corresponding to mth dark band. Now, T m and T m plus 1, both of them will depend upon this kind of expression will hold good. You will have d by L, right. D is the thickness of the wire, because of that you get the air gap. So, d by L that will be equal to theta, right, d by L that will be equal to theta, provided theta is very small. So, your T m plus 1 will obviously equal to d by L times x m plus 1. Okay. You take this x m plus 1 to the right hand side. So, that gives the thickness of the your air film, the film that you are having, which is made up of air, T m plus 1, and T m is refers to the thickness of the air gap corresponding to the mth dark band. This corresponds to m plus 1th dark band. So, from this what we have to do? We have to find the difference between x m plus 1 and x m, that is what we are going to do now. So, you have exaggerated picture. The L is the distance that separates the point where the two glass plates are in contact, the point O, and the diameter of the wire, that is you got the center of the wire here. This distance is L, because the wire only we are getting a wedge shaped film, right. L is important, L will come in the expression for the bandwidth. About two expressions that we had, T m plus 1 T m, you now have 2 d by L multiplied by x m plus 1 minus x m will be equal to lambda, because we had the expression for x m plus 1 and x m here. X m plus 1 will be the expression that you got, L divided by d multiplied by T m plus 1. Similarly, you will be having x m is equal to T m into L divided by d, that is what you are having here, 2 into d by L into x m plus 1 minus x m will be equal to lambda. X m plus 1 minus x m, as I told you, m plus x m plus 1 refers to what? The distance at which you get the m plus 1th dark band. X m is the point where you get the mth dark band. So, m and m plus 1 are the two successive bands, dark bands. So, the distance that separates the two successive dark bands obviously refers to the bandwidth. That is what you are having here, the bandwidth or the fringe width beta will be given by an expression of this kind, that will be equal to, you can take the terms here. So, this becomes beta, okay. 2 d by L into beta will be equal to lambda, okay. I think it is obvious, 2 d by L, this is the bandwidth or the fringe width, beta, but that will be equal to lambda, or in other words beta will be equal to lambda into L divided by 2 d. So, your d lambda L are constants. What is L? L is the distance that separates the one end of the glass plate to the center of the wire, and lambda is the wavelength of the monochromatic beam. We will be using usually a sodium vapor lamp. So, lambda is fixed, and d refers to the thickness of the paper or the diameter of the wire. There are constants, therefore, the fringe width beta will be a constant. So, for a given wire of a particular thickness, beta will be a constant, because lambda is a constant and other things are constants. Okay, this is a very important expression, you get the bandwidth. So, in a interference experiment, measuring the bandwidth, you see a microscope, you have the crosswire, keeping the crosswire at the mth band, m plus 1th band and so on. So, you can find the distance between two successive bands, that is given by beta. The beta is very important, the expression for beta is important. An air bridge is formed by inserting the wire, as all of you know by now, between the two glass plates. You use a monochromatic light to see the bands, as I told you. A travelling microscope is normally used to measure the bandwidth. You make the crossfire to coincide with the mth band, m plus 1th band, and so on. The thing that you observe here, there is a wire, this is a top view and side view, and the mth band, m plus 1th band, these things all of you know by now. So, you have here the fringe width is measured, that is what I showed you earlier. The fringe width is measured. Having measured the fringe width, you can rewrite the same expression. Instead of beta, you write the expression for d. So, obviously, d will be equal to now lambda L by 2 beta. So, what is the conclusion? If you measure the fringe width or the band width in the air bridge experiment, wherein you insert a wire of a particular diameter d, you are inserting a wire between the two glass plates. You got one glass plate here, one glass plate, you are inserting a wire, the diameter of the wire is d. So, the diameter of the wire can be accurately calculated using the air bridge experiment, because your d is connected to lambda. What is lambda? It is the wavelength of the sodium vapor lamp, that is known. L is the distance that separates the point where the two glass plates are in contact and the center of the wire. So, that is your L. Beta is the one that you have measured, right. Beta is the distance between two successive dark band or the bright bands, both of them will be same, that is the beta. Beta is the thing that you measure in the laboratory. So, knowing the value of beta, knowing the value of L and lambda, the value of d can be determined. So, this is a very important experiment in the sense that what cannot be measured by other methods. When a thin paper is there, the thickness of the paper is measured, those things can be measured accurately by the air bridge experiment, because the air bridge is obtained by introducing the paper or the wire. Here the phenomenon which makes us to measure the value of the wire thickness or the thickness of the paper is the phenomenon, the interference phenomenon. This is how the wedge shaped film was formed, and not only that, the plainness of a glass plate, whether the surface is optically flat, the plainness, whether you have given a glass plate, you have to ask whether it is optically flat. Optically flat means perfectly plain. You should not be having wavy edges, we should not be having the surface should be optically flat, it should not be wavy, right. By human eye cannot detect whether it is perfectly flat. So, what cannot be detected by human eye can be observed by the air bridge experiment. Supposing you want to test optical flatness of the one surface, you keep the surface here, the other surface that you are having here, that should be optically flat, right, that should be optically flat. Then you get a wedge shaped film here, but the thickness of the film will not be uniformly varying, because you have got wavy nature. So, the fringes that you obtain, instead of being straight as is shown here, the fringes will not be straight, they will be curved, they will be irregular in nature, there will be irregularly shaped structures be obtained, and thereby you can test the optical flatness of a surface. We have been seeing the phenomenon of interference and the effects which are produced by this phenomenon. When light rays incident on a wedge shaped film, wherein the width of the air film keeps on increasing. Similarly, what Newton observed, when you place a convex lens on the plain glass plate, you place a convex lens, what will you observe? You have a plate, the lens here, you got a plain glass plate, you place a lens here, what do you have here? You got air gap, right. Now, what about the thickness of the air gap? You see here the point, at this point the lens is resting on the glass plate, right. This is the point where the lens is resting on the glass. You have got a air film. We should be concentrating on the film here. You have got a air film here, and thicker is the air film. Note at this point it is this much. Here it is increasing. Something like air wedge. Here also the film thickness, thicker the air gap is increasing. Now we are going to see what is going to happen in the case of a convex lens when it is kept on a plain glass plate. You get rings which go by the name Newton's rings. These are the rings you will be observing when you have a glass plate and you place a convex lens. You eliminate the air gap by means of sodium vapor lamp, then you will be getting beautiful rings here, right. You see a bright region, you have a dark ring, then you what do you observe? You get a bright region here, the bright ring, dark ring, bright ring. This is the exact nature of the rings that will be obtained, that are observed by Newton, and so these rings go by the name Newton's rings. I will once again explain how these rings are formed, what kind of experiment setup one should have to obtain these rings, and finally, we have to know the radii of curvature, the radii of the dark ring, the bright ring, dark ring, the radii of the nth ring, bright ring, the radii of the nth dark ring, and so on. We have to obtain the expressions for these things, using which ultimately you can determine the wavelength of the light source. Let us go to the experiment setup as to how to get the Newton's rings. The experiment setup that is being normally used to get the to observe or to get the Newton's rings is shown in this diagram, wherein you find a source of light is there. Usually you make use of a sodium vapor lamp. You have a condensing lens, you have got a lens which condenses or increases the intensity of the light. It is incident on a glass plate which allows partly the light to be reflected and is made to go towards the lens air glass plate regime. That is a part of the light that is of concern to us. You look at again the light rays are incident here, light rays are incident, and the rays reflected by the glass plate. You got a G is the glass plate, reflected, and it travels through the lens, it goes here. You carefully observe this light ray that is coming here will be reflected back by the bottom of the lens as well as by the top of the glass plate. You have got a glass plate here, there will be for one light ray that is coming here, it will be undergoing two reflections. One is it is reflected by the bottom of the lens at this point, right, this is the point. Then another one which travels through the air gap, as in the case of air wedge, light ray travels through some air gap, here there is the air gap, then it goes through, goes to the glass plate, it is again reflected. So, these two reflected light beams will interfere. The important point is one light ray is undergoing reflection at the bottom of the lens, the another light ray is reflected at the top of the glass plate. These two will be interfering with each other. So, what is happening can be observed by an eyepiece. You can have an eyepiece here, right. So, let me again explain. G is the glass plate, L is the plano convex lens. You got a lens here, is a convex, is a plane surface, a plano convex lens. G1 is the beam splitter, it allows the light partly to go in this direction, that we are not concerned about that. We are concerned about only the reflected light, is a beam splitter. M is the microscope which is used to observe the Newton's rings. C is the focusing lens, a condensing lens. S is the light source, as I told you, S is the a monochromatic light beam, right, that is being normally used at the bachelor's level. You do this experiment, or in the high school you do the experiment on Newton's rings. Okay. So, a monochromatic light is allowed to fall normally on this film. What is this film? That is the air gap between bottom of the lens and the top of the glass plate, that is the air film. And now you get what are called Newton's rings. The thickness of the air film, it 0 at the center, but it keeps on increasing, and depending upon the conditions, as I told you in the case of air wedge also, at the for a thickness T m you get a dark band, T m plus 1 you get the dark band corresponding to the m plus 1th band. Okay. Similarly, here the thickness of the air gap, it keeps on increasing. Here it is 0, because the plano convex lens touches the plane glass plate. So, there is no air gap, the air gap is 0, but notice that the thickness of the air film keeps on increasing, and we are now concerned about this much thickness. At for this much thickness, whether you are going to have constructive interference or destructive interference. If you are getting constructive interference, you will be getting a bright point. Now, remember this is a circular thing. So, you will be having bright point and this will be again bright. So, you have a 2 dimensional thing, you have got a lens sitting on a plane glass plate. For all the points for which the same thickness is there, if you are going to have a bright point here, again you will be having bright point. So, if you look at the circle, you will be getting, for all the points you will be getting a corresponding a bright ring. That is how you get the bright rings and dark rings in the case of the experimental setup. So, the horizontal glass plate is kept at 45 degree inclination. This is the glass plate I am talking about, right, that makes the light to come in this direction. Okay. So, a plano convex lens of large radius of curvature about 100 centimeters is placed with its convex surface in contact with the plane glass plate. Air film is formed between the lower surface of the lens and the upper surface of the plate, as I mentioned just now. The thickness of the film is 0 at a point, right, that is important, and gradually it increases from the point of contact outwards. That I will repeat it again. At this point is 0, because the lens sits exactly on the glass plate, but thereafter the film thickness will be gradually increasing, that is what I am telling you just now. So, the film thickness gradually increases when you move from the center towards outwards from the center, and this is what I am showing here. At this point there is no air film, because the lens is sitting on the glass plate. As you move from here, the thickness of the air film will keep on increasing, and as in the case of air wedge, for a given light ray A B, what happens? This light ray gets moving in this direction, it is getting reflected at this point, right, bottom surface of the lens, right, that is the ray 1, right. Then part of the light ray will go and hit at the top surface of the glass plate, is reflected again backward, it comes here and it emerges out. The 2 light rays 1 and 2 are very important, like the case of air wedge, because we are going to use the same old conditions that we obtained for the condition for the bright band and dark band. These conditions will be applicable here also. So, we are concerned, as in the case of air wedge, that 2 rays 1 and 2, 1 is the light ray which comes from the bottom of the lens, whereas the light ray 2 comes from the top surface of the glass plate. You have got this is the thickness of the air gap here, right. The thickness, as I told you, keeps on increasing, right. So, for given thickness, say at this point what is the thickness, right. So, this thickness T m or T m plus 1, you will be getting the m plus 1th dark band or m plus 1th bright band. Here you will be getting m plus 1th ring and m plus mth ring and so on, right, dark ring. So, this is the interference pattern that you will be getting, the Newton's rings setup, how the lens is sitting on the glass plate. Again the rays 1 and 2 are the interfering rays corresponding to incident ray A B, the 1 and 2 are the interfering rays. The beautiful Newton's rings that will be obtaining, you will be having a bright region and a dark ring and a bright ring, dark ring and so on. The concentric circles will be beautifully seen through the microscope, whose radii ought to be obtained and the expressions of the radii ought to be obtained in order to determine ultimately the wavelength of the light source, which gives rise to this phenomenon of interference, which gives rise to the so called Newton's rings. So, we will move on to find the expression for the radii of the rings. What rings? The dark ring as well as the bright ring. Let R be the radius of curvature of the lens. You have got the plane of convex lens. As I told you, the radius of curvature will be about 100 centimeters. A is the center of curvature. There will be mth dark ring at a point corresponding to the thickness of the film T. Let me show the film, right, the thickness of T. So, at the point T, I told you that you have got lens sitting here. Here there is no air gap. The air gap keeps on increasing. Now, the thickness of the air film is T here, right. At this point I am talking about this point, which is at a distance r from the center. There is a lens that is sitting on the glass plate. This is the point of contact. This is your r, and at a distance r where you got a film thickness T. For the thickness T, whether you are going to get a bright band or dark band, it depends upon the condition that we have already obtained. Okay. So, anyway, we are concentrating on the thickness of the film T, and depending upon the condition we will be getting the mth dark band or the bright band and so on. Let me now summarize as to what we have understood from this lecture. We now have the diameter of the wire, a thin wire can be obtained by knowing lambda and measuring the fringe width beta. Newton's rings are obtained as in the case of air wedge because of the air gap that exists between the lens, the plane of convex lens, and the plane glass plate, because the air gap you are getting the Newton's rings. We will move on to the questions. How will you determine the thickness of a thin wire or paper using the air wedge experiment? Question number 2, how are Newton's rings formed? With this we come to the end of this lecture. In the next lecture we will see the expressions to be obtained for the radii of the bright and dark rings in the case of Newton's rings, and from there how to obtain the lambda of the source of light. Thank you.